Part 4, and this is for questions 31 to 40. Question 31, considering only structure isomers, what is the number of alcohols of each type with a formula? This one here, we are seeing primary, secondary, tertiary. Okay, let's begin with maybe primary. These are 5 carbon atoms, so I can have CH3, then CH2, 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 CH2OH. Okay, this is a primary alcohol. Now, hydrogen's 12. Let's see, this is 5, 7, 9, then 11, and then 12. Okay, cool. Now, next, I can shift this one here, and then I put it here. Now, that is chain isomerism. I can shift it, and then I put it here. Okay. Then I can also, yes, I can shift it and put it here, or I can put it here. So what do we get from those two? I'll now get, of course, this one now will have a CH3. So CH3, then C. This one, which has 2 hydrogens, now will remain with 1. So there's a methyl here. So 1 hydrogen here rearranges and then comes to this one. So that's why this one becomes the CH3 here. Okay. Then from there, we have CH2, then CH2OH. You see that? I can also have CH3, H2, then CH, then CH3, like I said before. You can put this one here. Then, actually here. You can put it here or here. Then after that, we shall have a CH2OH, not so? Those are all primary alcohols. There are 3. But still, we can have this one put here, okay? And then this one will now become a CH3. So we shall have a CH3 here. Then C, this hydrogen will go away, and then it comes to this one here. That's why this one becomes a CH3. You see that? Then we shall have a CH3 here, then a CH3 here, and then CH2OH. Okay, this is 2,2-dimethyl propan 1O. You see, still primary what? Alcohol. There are how many? We have gotten 4. That means I have to center here on B and C. Then let's go to secondary. Just move this one maybe onto that. So we can have CH3, CH2, then CH2, okay, then COH, then there will be hydrogen here, and then CH3. So I moved this one here, okay. Now, that one we call it positional isomerism. We are looking at the position of the functional group, okay. Then from there, the secondary alcohol must have the OH on the second carbon. Now I can shift this one and then put it here. So that means when I shift this one and I put it here, a hydrogen here is going to shift and come here. Then we shall have the CH3. This one has become the CH3, okay? Then CH, then here we shall have the CH3. You see that? Then CHOH, and then CH what? 3. Is there any other that we can have? Let's check and see. And by the way, when you write this OH on this one here, okay, on this one here, at first, this will still be, because this one is which one? 1, 2, 3, 4, 5. This is pentan 2O. Even when you put the OH here and it is not here, now the counting will begin from this side because the functional group is supposed to take the lowest number. So still that one will be propan 2O. So I mean pentan 2O. So when you put the OH here or here, it is going to be the same. Okay, now suppose I also shift this OH, okay, and I put it onto this one here. I will have CH3, then CH2, C, then put the OH here. Then here I'll have a hydrogen, and then CH2, CH3. Remember, a primary alcohol is supposed to have, if this is the OH, we are supposed to have 2 alkyl groups, okay? 2 alkyl groups, and then there's a hydrogen. So this carbon here holding the OH should have 2 alkyl groups on it, okay? So This is an ethyl and this is an ethyl. That one is also a secondary one, alcohol. Okay. So those are the three that we are having here for secondary. There are three. So we have four, then we have three, and tertiary. So for tertiary, we are supposed to have a carbon, then with the OH, then we have three alkyl groups. You see that? I can actually get it from where? From here. Suppose I take this one here to this. That means I will get CH3 here. Then here I will also have CH3. Then here I can have CH3, CH2. That is the tertiary alcohol we can get there. Is there any other we can get? If let's say we were using this one here, and maybe you shift this, the whole of this ethyl, and you put it here, so you will see that still you're having an ethyl group, then a methyl group, and then a methyl group. It's the same. So you are only going to get one tertiary alcohol, okay? One tertiary alcohol, which is here. So that means our answer is a C. Question 32. Which structure represents part of the polymer chain PVC? Now, PVC in full, it is called polyvinyl chloride. Now, this one, the monomer is, it is called chloroethene. Chloroethene is drawn like this. Draw a molecule of ethene. So we have H, then one of the hydrogens is replaced with what? Chlorine. This is the one here. So we have to see which one has that monomer, okay? When we look at the first one here, break this backwards, so you close it in. Remember, when we were forming the polymer, these ones do by breaking outwards. You see that? So now I bring them inside. So this one, no, this one will go like that, then this one like that, then like that, then like that. So what do we get from here? We have a hydrogen here, a hydrogen, then there is a double bond created here, then there is a chlorine, and then there is a chlorine. You see that? If we can continue, now this one has been broken, this bond has been broken here. Now do you see that this is the same thing as what we are having here, and also this one here? So they are all going to give you this one here. So meaning, since this one is coming from this monomer, actually there is something wrong that I wrote here. This one is a hydrogen. We have a chlorine here and then a hydrogen. Pardon me there. Now, we are getting this monomer that we are supposed to get. So that means the answer is actually A. For this one, if you do this and then this one here, you are going to get carbon, hydrogen, then there is chlorine here, double bond, then there is chlorine. This one is dichloro. So we are seeing some dichloro. That one automatically disqualifies it. Even this one, we can see a dichloro. Yes, here there is going to be this chloroethene, okay? But then here there is ethene, and then here there is this monomer here. So here there are two different monomers, and we are supposed to have one monomer, which is chloroethene. You see that? That's why even this one is off. Then when you come to this one here, it is also off. So our answer is A. Question 33. A possible mechanism for the exothermic hydrolysis of 2-chloro, 2-methylpropane, this is 2-chloro, 2-methylpropane, is shown. This is the slow step. This is SN1 because these are three alkyl groups, so there is a greater positive inactive effect. So what happens? This is partially positive because chlorine is more electronegative compared to carbon. So this one goes off, and then it gives you this carbocation. Okay, so this is the slowest step, or the rate determining step. Now they are saying which diagram represents the reaction pathway diagram for this mechanism. This one is very fast because after this one has attained the positive charge, then it will immediately react with the OH. So it's a fast reaction there. And then when we look at these pathways here, where it is an exothermic reaction, so we expect we call them the products to be with less energy compared to the reactants, okay? Because the system has lost energy to the surrounding. So what is remaining is therefore having very little energy. So when you look at all of these ones here, of course, this one is endothermic, so it has to be off. And this one is exothermic, this one is exothermic, even this one is exothermic. But since this one is a two-step mechanism, we can see the first one here, the slow step, okay? So we are seeing high activation energy here needed to first break this one off, okay? And then from there, they form this intermediate. Now this intermediate reacts with this to convert into the products. So because it is a two-step mechanism, then we are going to take our answer as a B. Why as a B? The first one has to be high activation energy to form that what? To form the intermediate there, the first intermediate. And then this one comes in here, okay? That is the second one here. So that is supposed to be that. But you can see that here the second one has a high activation energy. It cannot be higher than the first one, yet this is what? A first step. Okay. So the first one is the one which is slow with the higher activation energy. Of course, this one is wrong because there are three of them and we are seeing only two steps in there. You see that? So our answer has to be the B there. Question 34. Compound W contains atoms of carbon, nitrogen, and hydrogen. Compound W reacts with HCl to produce propanoic acid. Which row is correct? Okay, we are seeing an amine and a nitrile. That one has to be a nitrile, okay? Because when you get a nitrile, like, let's say we are producing propanoic acid, that means we must have propane nitrile. So CH3, CH2, then CN. You see that? Then you put dilute HCl, so we put HCl and then water. Then what we get is CH3, CH2, COOH. So this process, we call it hydrolysis, okay? Then we have, what else? We have an ammonium chloride that is formed here. Now, if we are to balance, you can see that these are two oxygens here, and here we are seeing one oxygen. So to balance that, I will put a 2 here. Hydrogens, these are 4, okay? If these are 4, then plus 1, these will be 5, okay? These ones will be 5, then plus how many here? Plus 5, and those 10, so those are 10 hydrogens there. Then when we come to this one here we're having 5, and then 6, then plus the 4, 10. So it's balanced, okay? Now, propane nitrile, this is the one that has given us the propanoic acid here. So where is propane nitrile? This is the one here. Okay, so that means our answer is D. When you look at ethane nitrile, you are going to get CN here. So the carbon in here is also taken. So don't think that propane nitrile, you are going to have propane here, first of all, the propyl group, then you put on the nitrile. No, the carbon in the cyanide here is also counted all through. Okay, so now this one will be butane nitrile. You see that? Then after that, for ethane nitrile, we shall have also HCl here, then plus 2 water. Then you will get ethanoic acid instead. You see? Then plus the NH4Cl. This is ethanoic acid, so that one will be off. Now, let's look at an amine. So let's say we are using, let me begin with propyl amine. So propyl amine, this is CH3, CH2, CH2, then NH2. So when you add HCl, of course, this is an acid-base reaction, so we are going to get a salt. This one is a base. It has a lone pair, so it can donate to the hydrogen ions there. Okay. Then that means we can have CH3, CH2, CH2, then NH. 3, then Cl. Okay, NH3Cl. So that is the salt we are getting. But with ethane here, ethylamine, you'll get the same thing here. I'll just copy this. Same thing here. Then I take out a CH2. No, say CH2. So that is what we are getting here. Then I just shift this, put it there. Okay. Now we are not getting propanoic acid. So these two are wrong. So we are not supposed to pick from amine. We pick from the nitrile. And the one that gives us propanoic acid is propanitrile. Question 35. Two reactions are described. 2-bromo-2-methylbutane heated with sodium hydroxide, aqueous sodium hydroxide. Now here we get an alcohol. It's a substitution reaction. What is 2-bromo-2-methylbutane? So we have 1, 2, 3, 4. 2-bromo, 2-methyl. Then butane, so CH3. Then CH2 here, CH3. So that is what we are going to have here. And it is the same thing I'm going to have for the second one. But where there is bromine, I'm going to replace it with what? With a chlorine, because they are saying 2-chloro-2-methyl. Okay. Then in both reactions, the conditions are the same and sodium hydroxide is in excess. Now, when you add sodium hydroxide here, all of them are going to give us the same alcohol. So we are going to have this one here, okay? But where there is the halogen, just replace it with the OH, okay? That is what we are getting there. And they are saying that 30.18 grams of 2-bromo-2-methylbutane forms 12.32 grams of product X. This is product X, okay? Then the MR of 2-bromo-2-methylbutane is 150.9, and then for this one is 106.5, which row is correct. They want the percentage yield of X here, and then the relative reaction rate that is faster. So which one is faster than the other? Now, when we look at these ones here, this bond here, the carbon to bromine bond, is weaker than the carbon to chlorine bond because chlorine is more electronegative compared to carbon. So it tends to pull the bonding electrons towards itself here. So this bond is stronger than this one here, okay? And also bromine, maybe the other explanation I can use actually, which is better, bromine is bigger in size compared to chlorine, okay? So because of this large size, then the nucleus is far away from the bonding what? Electrons. The nucleus of bromine is far away from the bonding electrons, so we are going to have a longer bond. And we call it the nuclear attraction, okay? For these bonding electrons here, it is going to be weaker in bromine compared to chlorine. So this one will be very, very weak, and therefore the rate of reaction is going to be faster with the bromine compared to the chlorine. You see that? Okay, so that is what we are having there. So where there is bromine, it is faster. So 1 has to be faster than 2. So I have to look here and here. Are we there? Now let us look at the yield here, the percentage yield. Now, when we react these ones with sodium hydroxide, okay, we are putting sodium hydroxide aqueous, also here sodium hydroxide aqueous. So we are getting the reaction mole ratio is 1:1. Now let us look at the moles of the 2-bromo, 2-methyl butane. So this one is going to be, they told us 30.18. Then divide by the MR of this one, which is 150.9. So this one is equal to 30.18 divided by 150.9. This is 0.2. Okay, 0.2. So since the mole ratio is 1:1, that means these are the same number of moles of X that are formed. Are we there? So moles of X, okay, formed is also 0. What? 2. You see that? Then from there, let us get now the percentage yield. We have to get the mass. So mass of X formed, it is going to be this 0.2, then times the MR of X. So what is the MR of X? How many carbons do we see here? 1, 2, 3, 4, 5. So 5 times 12, that one will give us a 16 answer. So 5 times 12, then plus hydrogens, these are 3, and that will be 5, then 8, 11, and then 12. So we shall have a 12 here, then plus 16 for oxygen. So this is 60, then plus the 28, that is 88. Then when we multiply by 0.2, what do we get? 0.2 times 88, that is 17.6. 17.6 what? Grams, okay? This is what we expect to get, okay? Expected mass to be gotten from here if we are reacting these grams of 2-bromo-2-methyl what? Butane. But we got out what? 12.32. So that means the percentage yield is going to be that 12.32, which came out of the 17.6 we were expecting, then times 100. So what do we get here? 12.32 divided by 17.6, then times 100. This one gives us 70%. 70%, which is here. Remember, we are looking at option 1, A and then C, but this one has given us. So that means our answer is C. Question 36. An alkene P reacts with an excess of hot concentrated acidified potassium permanganate. Here the double bond actually in the alkene is broken completely, and then oxidation takes place on these carbons that were in the double bond. Okay, then of course if it is cold dilute acidified potassium permanganate, then we get a diol. You see? So they are saying methyl propanoic acid is the only organic product. What is alkene P? Now let us look at these alkenes which are given. This is hex 3-ene. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3. So hex 3-ene will be there. Then 2, 5. So 2, there will be a methyl here. So CH3, then this will be CH. Then of course here we shall be having a hydrogen. We shall have a hydrogen on this one here. So CH, then CH here. Then this will be the 5, so we shall have the methyl group there, then CH, then CH3. Something like that, okay? 1, 2, 3, 4, 5, 6 carbons. Then from there, when we cut this one, when you oxidize using hot concentrated acidified potassium permanganate, you're going to get CH3, C, then CH3 here, then H, then C. First of all, this one will be oxidized and it goes to the, we call it the aldehyde. It will go to the aldehyde, but then the conditions are harsh, so it will go to a carboxylic acid. You see that? And even this one, it is the same. CH3, CH, CH3, then COOH. You see? So we shall get two molecules of this. And this is 2-methyl propanoic acid. 2-methyl propanoic acid. And actually, even if we don't say 2-methyl, because we are not going to have 1-methyl propanoic acid. So that's why they don't put that 2 there. So it's therefore methyl propanoic acid. So I think the answer is A. But now let's look at B. 2-methyl but2 in. So but2 in is 1, 2, 3, 4. So we are going to have a double bond here. Then there will be a hydrogen here. There will be a hydrogen there. Let me make it a little bit better. So I'll have a hydrogen here. First of all, this is a CH3. So 2-methyl. The methyl group then has to be on this one here. So meaning I'll take out the hydrogen from here. Remember, carbon is supposed to have how many bonds? 4. So we have that CH3 here. Then when you oxidize this one here, so this one will go to a ketone. We shall get CH3, then C, this one here, then CH3, then this one will give us ethanoic what? Acid, CH3COOH. You see that? And we are not getting methyl propanoic acid. So this one has to be off. Let's go to methyl propene. This is CH3. Then we have a CH3 here, double bond. Methyl propene will be this one here. You can set 2-methyl propene, but you cannot have this one put on the first one here and you still have what? And you have something like 1-methyl propene now, just like I said for this one up here. So we oxidize this one here, we shall get CH3, C, then O, then CH3, and then plus, of course here this one will be methanoic acid, but it can be further oxidized by hot concentrated acidified potassium permanganate. Then you get carbon dioxide. You see that? And actually water. So that is what we get there. Then how about this one here? So even this one is off. How about this one? Oct 4 in. Oct 4 in, you are going to have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Then for oct 4 in. So the double bond will be here. Then CH2, CH2, CH3. Here. Same here. 3, then 2, then 2. Then this one will have a hydrogen. Okay. And when that one has a hydrogen, even to also complete the bonding here, for carbon, we shall have a hydrogen. Then when you break that one into 2, you'll get CH3, CH2, CH2, then COOH. There will be 2 of them because this one is symmetrical. This one is the same as that. Now, you can see that this is butanoic acid, but this is methyl propanoic acid. So even this one is off. That's why our answer is A. Let's go to 37. 3 substances are listed. We have butane, hydrogen, and hydrogen bromide. Then they are saying that which substances are possible products of the free radical substitution reaction between ethane and bromine. Now, between ethane and bromine, there will be formation of hydrogen bromide. Okay, that is when you have, let's say, by the way, first of all, we begin with, let me take you through the process. We begin with what we call initiation. Okay, the initiation step here, we are going to have bromine. Okay, bromine here, breaking homolytically to form 2 radicals. These ones are highly reactive. They cannot be there on their own. So now this one attacks the molecule of ethane. So ethane is CH3, CH3. Okay, but what I'm going to do is to write the hydrogens like this. Then I project this one here. So when this one comes here, it will scoop off this hydrogen from here, and then that. So we are going to have something like this. This one also breaks homolytically like that. Now, in there, by the way, this is what we call propagation. Propagation. So in the propagation step, we see a radical, okay, attacking a molecule. Then we form a new molecule, and then another radical. So we produce more radicals. So here we shall get CH3, then CH2. This one is a radical, okay? Then plus HBr. So do you see the hydrogen bromide formed? Now this one can continue. Then we have this one can continue. It attacks a molecule of this again. You form another molecule, okay, and then another radical. So it goes on and on. That is propagation. But we have termination step where two radicals come together. So there is a possibility of this one here, okay, coming together with another one radical, which is also CH2, CH3, because these are many molecules in that compound. So these ones come together here and they form this bond CH3, then CH2. The compound that comes out of this will be actually butane. So there is a possibility of getting butane, but we don't form hydrogen, okay? We don't form hydrogen, but we instead form what? HBr. So we don't have where, like you have the two radicals of hydrogen coming together. No, we don't produce radicals of hydrogen. So hydrogen is always scooped from the molecule, from here, okay? And then it forms the HBr there. So that means wherever there is two, I cancel that right away, okay? Wherever there is two, so there is two here, there is two here, there is two here. So 1 and 3 only. That means the answer has to be C. Question 38. The structure of the testosterone molecule is shown here. This is the one here. Which statements are correct? They're saying the carbon atoms C1 and C2 can be oxidized with acidified potassium dichromate. This one is already ketone. It cannot be oxidized any further. Okay, so that disqualifies 1. So wherever there is 1, I'm just going to disqualify. So A is off. This one here is a secondary alcohol. There is a hydrogen here. So this one can be oxidized to now a ketone. So oxidation can happen here, but not here. And they said these two can be oxidized. So that one is off. Then option 2, there are fewer than 27 hydrogen atoms in one testosterone molecule. Now, when we check this molecule here, there is a carbon here, but I'm not going to write the carbons, okay? Let me just write the hydrogens. So there are 2 hydrogens here, there are 2 hydrogens here, and how about this one here? This is 1, then 2, 3. There has to be a hydrogen here. So there is a hydrogen here, a carbon here. This is 1. These are 2, so that will be 3, 4. There we don't have a hydrogen, okay? Then here, the same thing is 1, 2, and then these 2, so that is 4. Then we come to this one here. There's a hydrogen, a hydrogen, a hydrogen, a hydrogen. Then here there will be 1 hydrogen, even here 1 hydrogen. Here we don't have, the bonds are 4. Then here there is a hydrogen, there is a hydrogen here, here. Then there is 1 here, there is here, here. Then there is 1 here. Now this is skeletal. So for any skeletal structure, the carbon atoms are hidden, okay? They are hidden in that chain or the ring. But these ones which are attached to the ring as substituents, these ones are shown from, we call them what? Those alkyl groups that are connected there, or the functional groups. But those ones are shown. Even the hydrogen that is attached to this oxygen is also shown. Or maybe you have an amine or whatever, okay? But the hydrogens that are directly connected to the carbon in that compound, okay, like this one here, is always, those hydrogens are always what? Hidden. Now here, they would even just put something like that. They put this one off, just a stick like that, meaning there is a carbon here with the 3 hydrogens, okay? Now let's count the hydrogens. These are 4, then this will be 7, Okay, then 8, then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Then this will be 24, 25, 26, 27, 28. There are 28 hydrogens, and they said there are fewer than 27, and yet there are more than 27. We have 28. So that means this one is off. So wherever there is a 2, I will also cancel. That means our answer is D with only 3. But let's check 3. There are 6 chirocarbon atoms in one testosterone molecule. Okay, let's check again. The chirocenters. A chirocenter is that carbon that is connected to 4 different groups. Okay, so there is this one here is a chirocenter. In fact, let me use red. This one here is a chirocenter. Okay, where else do we see a chirocenter? There is a chirocenter here because this group is different from what is going this way, and also the hydrogen. You see that? Just like this part here is different from what is going this way, and also the methyl. Okay, then next, so those are 2. There is another one here. This part is different from this, and the hydrogen. So those are 3. Then there is another one here. This is different from this, and then the hydrogen. Okay, those are 4. Any other? There is another one here, the OH group, different from what is going this way. The environment here is different, and also there. So that is the 5th one, and then there is a 6th one here. Okay, this one is different from what is this way, and there. So there are indeed 6 chiral centers. So that's why it is only what? D. That is correct. Then question 39, the structure formula of hept 1,4,5 triene is shown here. Now you can see that here we are going to have a carbon, then a hydrogen, double bond, carbon, then put a hydrogen here. Then there is C here, there is CH, then CH2. So we shall have CH2 here. Then the next one is C, then H, then double bond. Then we are seeing a C, then another double bond here with a C here, and then H, and then CH3. CH3 is here, then the hydrogen, then there has to be a double bond between these 2 carbons. Yes. So I think that is that. It's a 1, then 2, 3, 4, then 5 triene. Okay, and then the question is to do what? How many of the carbon atoms in one molecule of this are sp2 hybridized? So for sp2 hybridization, we see 1 pi bond and 1 sigma bond. Okay, we have 1 sigma and then the pi, which we represent like that, the sideway overlap of the p orbitals. So it is here, this is 1, 2, those 2 carbons there. Then we have this carbon here, okay, and this one here. Now when you look at this carbon here, for it, you must have 1 sigma bond and 1 what? Okay, between those 2 carbons, but maybe I can say if it is sp2, a p orbital, I mean p as a subshell has 3 orbitals, and then s as a subshell has what? 1. I mean has 1 shell. So we have a hybridization that has taken place. Remember, carbon has gotten 4 electrons in the outermost. So it is 1s2, 2s2, then 2p2. So the 2 electrons that are in here, one is one is excited and it is given to P. Then they become degenerate. They are on the same energy level, but at first they are like this. P is slightly higher. Okay, so that is that. Now sp2, it means that we are going to use 2 electrons from here to bond. Okay, just like maybe let me refer to these ones here. So you will get one hydrogen coming here. Okay, one hydrogen coming here. Then this carbon will bond with this carbon here. Okay, so it will bond with another carbon here. 1, 2, 3, 4. Okay, so they will bond. Okay, so I mean that is head-on overlap of the p orbitals, something like that. You form that. Okay, then after that, this one that is remaining, even this carbon here now has gotten a hydrogen that bonds to it, and then it also bonds to another carbon here. Okay, there's another carbon then continuing. Then here there is this bond here, sigma, and then there is sideway overlap of the p orbitals to form the pi bond here. Now, before the sideway overlap, how many sigma bonds are formed? This is 1, 2, 3. 2 are coming from the p, and then 1 is coming from the s. You see that? So it becomes sp2. 1 from the s, 2 from the p to form the sigma bonds before the sideway overlap to give you the pi bond. You see that? That's why we call it sp2. Now, for this one here, it overlaps this way and also this other side. So it has 2. It has 2 pi bonds. For us, we are looking for 1 pi bond. So that means it is this carbon here, and this one, and then together with this, but not this one here. So how many are those? There are 4. That means our answer becomes A. And then lastly, question 40. They are saying hydrocarbon X is saturated. Each molecule contains 1 ring of carbon atoms. The mass spectrum of hydrocarbon X is measured. The peak representing the M plus ion is 14 millimeters high. That is the relative abundance. Okay. The peak representing the M plus 1 ion is 0.77. So the moment you see M plus and M plus 1, always think about finding the number of carbon atoms. Okay, number of carbon atoms, which we find using this formula, 100 out of 1.1, then times we have the relative abundance of the M plus 1 ion, then divide by the relative abundance of the M plus ion. So this will be 100 over 1.1, then times the relative abundance of this one here, the M plus 1 ion is 14, and then the M plus 1 is 0.77. So putting this in the calculator, what do we get? 100 out of 1.1, then times 0.77 out of 14. It gives us 5. So 5 carbon atoms. But then they're saying what is the mass to charge value of the M plus 1 ion of X. Okay, now from here, of course, we shall be looking for the molecular mass of this ion. So what is it going to be? Now, they are saying it is a ring of carbon atoms, and there are 5. That means we shall look at a pentagon, maybe. So each carbon here has gotten 2 hydrogens. So we have a hydrogen here, because remember it is supposed to have how many? 4 bonds around it, not so. So what we are having here is a hydrogen, and also here, that one there. Then we have those carbon atoms. Now, carbons are 5. So we have 5 times 12. Isn't that 40? No, that is 60. Come on. So 60 then plus hydrogens, 2, 2, 2, 2, 2. That is 10, not so. And the relative molecular mass, I mean atomic mass of hydrogen is a 1. So we have 60 here, then plus the 10, which gives us what? 70. That means our answer is C. So this has been it for this paper. Thank you so much for watching. May God bless you and see you in the next videos.